I started like a little later, I wasn't
This one.
like I was doing all engineering classes. And so like if I start earlier, then I could at least get like a minor.
Are you definitely?
But like if I I just
I don't know about that.
like if I did or probably minor and applied and then maybe throw in another minor because I would have like extra weight in class, not because the senior project might be time probably theoretical. Like if I had it my way, I would probably go apply math major and then I could
It's like not hard.
wait on grad but it's just like the I don't know, like I look into the salaries that each make the level of education. And so like if I did apply math and I stopped at undergraduate and I went and got a job, I would
You can do a lot of that. Like you can work in like
but I don't want to work on it. Like I think like
so like,
yes, but it's like I don't want to just like
that's what everybody's saying. Me too. But like I'm worried of doing the math office hours where I go and it's like 30 people to I know
But also it's like,
and like I feel like
my math office hours are 9 a.m.
Okay, good morning everyone. Okay, let's get started. So, welcome back for anomalous week, last week. Back to the remaining third of the semester. I'm going to jump pretty much straight in. Just a reminder that everything is on the regular schedule this week. And I hope to return the second midterm on Thursday morning. Just as an FYI, I heard this as I was leaving the house this morning. Apparently something big's happening later this week in not the most exciting area of physics, but the definition of the kilogram is about to change. There you go. So, if you're interested, after more than a century, the kilogram is moving from being defined by reference to a block of some exotic material in Paris to being based on fundamental constants. So stay tuned, I think it's happening on Friday. Okay. Alright. So I know you can barely contain your excitement over the news of the change in the definition of the kilogram. There we go. Okay, so we're going to talk relatively briefly about two topics this morning. First is static equilibrium, which you already know something about. So I just kind of quickly want to recap the important concepts. And then we are finally moving away from analysis solely of really rigid objects, even though in a sense we've a little bit allowed for objects to change shape when we talk about angular momentum and changing rotational inertias, but we're specifically heading this morning and into Thursday and early next week into looking at materials that are not rigid. In the first instance today, we're going to look at materials that would broadly be classified as solids, but are not totally rigid. They can be deformed, they are elastic. So we'll spend just a very short amount of time about that. And then starting on Thursday morning, we're going to turn our attention to fluids, which will occupy us for a little more than one session. And then our last two topics of the semester are gravitation and special relativity. Okay, so that's the roadmap for the remaining 4 weeks. So let's come back to static equilibrium. Not on the face of it the most exciting topic, because nothing's happening, at least if things are going well. Many of you are future engineers, so in fact the topic of statics is of a lot more importance for you, because in many cases you'll be dealing, or at least if you're in the sort of mechanical engineering realm, in the other areas of engineering, you'll be dealing with objects that you would like to remain static under various types of forces and torques and so on and so forth. So while in a sense it's not the most exciting thing, it is nevertheless important. So with that preamble, what are we talking about? Objects that are in static equilibrium. Well, first off, they're in equilibrium, which means there are neither no net forces nor no net torques. Second line down up there somewhere. That's our definition of equilibrium. However, of course, that's not all that's required for it to be static equilibrium. It's entirely possible for objects to have no net forces and no net torques acting on them and be moving. Okay? This means they're moving at a constant velocity, both linearly and rotationally. So the static part of this adds another constraint, which is in fact there's no velocity, there's no motion, either linear or rotational. Okay? So equilibrium, second word in that expression up there, relates to the second line, the constraints that are imposed there. And then static, the first word in that phrase, relates to the first line in those constraints. Okay? So, concise way of defining this. Okay, so objects at rest, no net forces, no net torques. There are in fact two subcategories of static equilibrium that we'll need to worry about. So-called stable and so-called unstable static equilibrium. And the easiest way perhaps to show you what this means, and then we'll just write down briefly what it means in words. This is not the easiest thing for all of you to see, but as you can pretty much see even from a distance, it's a large concave bowl. Got a small spherical ball here. I place it at the center, and it is not moving. It's not rotating, so it's certainly in static equilibrium, so there are no net forces, no net torques acting on it. It's definitely in equilibrium. The question of whether it's stable or unstable equilibrium has to do with what happens if I perturb it a little bit from its existing current position. And so if I perturb this a little bit, after a little bit of a disturbance, it will make its way back to its original static equilibrium position. So a small perturbation has it return to its original equilibrium position. This is not just a ball, it's obviously a large mirror, so I'm hoping I don't drop this. Let's flip it over. Now I have a convex bowl. And somebody kindly shaved the top of this to make this a little bit easier. So still satisfies almost static equilibrium conditions, constraints, but of course if I perturb this now, it does not go back to its original equilibrium position. So stable versus unstable equilibrium. Stable means it returns after a small perturbation, disturbance, and by contrast, this does not return. Okay, so it returns and does not return. So just be aware of the difference between static equilibrium and its two variants, stable versus unstable. Okay, so let's see if we can quickly sort of do a worked example on this. I know you've got several on this week's problem set, and I will say right now, and perhaps if I remember at the end of class, I put a bunch of worked examples in my notes on this topic. I've already taken a look at it. I'm doing some homework problems, but rather than spend too much time on this in class, do take a look at those worked examples in my notes. So what's our problem-solving strategy going to look like typically for working problems? And this is all stuff you know. So in that sense, it's relatively straightforward. And there'll just be a couple of sort of hints along the way or tips along the way to sort of try and make this as simple as possible. By and large, we will work in problems that are in 2 dimensions. So usually 2D situations. Let's call it in the XY plane. And so the constraints that I have over on the chalkboard on the right-hand side would then become the following. So I could say that the net force in the x direction is 0, net force in the y direction is 0, and the net torque, and let me just leave that for a moment, is 0. As you know, we have this sort of duality or complementary ways of describing directions of torque. If we've got motion in an xy plane, or at least potential motion in an xy plane, I could describe rotations or torques as being clockwise or counterclockwise from whatever perspective I'm taking. But as you know, we're also allowed to, and often encouraged to, take this sort of right-hand rule-based definition of torque as well, which is to say that it can be either out of the plane of the xy, chalkboard in this case, or into the plane. So with that sense, I'm going to write this as the net torque in the z direction should also be 0. Okay? So it's just a slight elaboration of what's over on the right-hand side, assuming that we're working in the xy plane. All right, so let's carry on with our strategy. So select object to study. There may, in some cases, be several objects. More often than not, there's kind of one obvious object of interest. So this might be object, and if it is, we'll come back and sort of repeat this as we've done in the past. We're going to draw our free body diagrams. So draw free body diagram plus all forces acting, and implicitly in here maybe some torques. And then you will define our coordinates as usual, resolve any forces if needed. And at this point we should be, make sure I haven't got anything wrong here. Yeah, let's repeat as necessary. Let me just put that in just in case. More than one object. And then solve the equations that we've arrived at. Okay? So very straightforward problem solving strategy. And again, much of this you know already, so I think we can be fairly fast. What I'm going to do is simply take an example of this, work through it, and at one point at least point out something to keep in mind as a kind of aid or tip to make this thing go a little faster. Okay, so here's the setup. Let's say we have a straight ladder leading up against a wall. Let me grab some parameters here, make sure I get this right. Okay, so we've got a ladder of length L. Of course, I'm going to write down some variables here in just a moment. Leaning at an angle theta with respect to the floor. We also have a person standing on this ladder. And they are standing a distance d up along the ladder as measured from the bottom. And let's see, this person has a certain mass. I guess I'm just going to write this on the side. So let me write some parameters here. The total length of the ladder is 8 meters. The weight, so this is mg, of the ladder is 355 newtons. The distance d of the ladder at which the person is standing is 6.3 meters, and the weight of this person, again mg in this case, is 875 newtons. Theta is 50 degrees. What else do you need to know? The wall is smooth. and the floor is rough, so there is friction. Okay, so that's our setup, and this problem actually wants us to find the following thing. It wants to find the forces exerted on the ladder by both the ground and the wall. Okay, so this is a static equilibrium problem, which means things are at rest, nothing's moving. That's the setup. Okay, so we're asked to find the forces exerted on the ladder by the ground and the wall, respectively. Let's see if we can quickly follow our problem-solving strategy. Okay, so object of interest. Clearly, the primary object of interest here is going to be the ladder. So we're going to kind of focus our attention on the ladder, and maybe highlight it just to show that. So there's our object of interest. So our next task is going to be to find all of the forces acting on it. Okay, so help me out with this. Talk me through what forces act on that ladder. Yeah. Downward force of the person. Okay. And this is going to be a case where we assume the person is point-like, and we assume that their weight is acting at the effective sort of center of mass, possibly center of gravity, which we'll talk about briefly in a few moments. Okay, so I'm going to take a point which is a length d, distance d up the ladder. Let me highlight that with a red dot. And I'm going to assume that their weight acts vertically downwards, and we're already given what that is. It's WP. Okay, so there's one of those. What else? What else acts on the ladder? Yeah. Weight of the ladder. Okay, good. Where can we assume the weight of the ladder to act? I didn't explicitly say this, but when it isn't stated, you can probably assume. Yeah.
It'd be in the center, so like 4 meters.
Center of mass, or center of gravity, which again we're going to talk about in a few moments. So yes, I'm not going to draw it on here, it's already pretty busy, but this is halfway up, and this now is the weight of the ladder. Again, we're given that, okay? So we know a couple of forces, we know the points at which they can be assumed to act. What else? What else acts on this ladder? Yes. Force on the ladder from the wall. What can you tell me about that? Okay. So, yes. A normal force, if you will. So this ladder can be assumed just to be leaning against this vertical surface. So let me call this the normal force exerted by the wall on the ladder. Anything else at that point before we move along? Go ahead.
There's also a friction force, so it's prevent the ladder from
Okay, friction force working that way, and at what point is it acting?
when
Okay, good. I'm going to write this F sub S to denote a static friction force. Okay, anything else? Yeah.
Normal force from the floor to the ladder.
Good. Normal force from the floor to the ladder, pointing in which direction?
Directly up.
Okay, vertically upwards. Good. So the normal floor force of the floor on the ladder. Anything else? Okay, that certainly exists, but keep in mind that, as always, when we draw free body diagrams, we're always focusing on one object at a time. But right now, we're talking about forces acting on the ladder. Now, have we been worried about forces acting on the person? Yeah, for sure. But for now, we're just worrying about the ladder. Anything else? Yeah. Okay, so friction going up against the wall. So good, good in a sense, because I wanted somebody to raise it, this possibility. You might imagine in general there is going to be a friction force there. However, in this rather contrived artificial case, I'm claiming that the vertical wall is totally smooth. So in that case, we don't have a friction force, okay? But yes, I want you to be thinking about that in general. So as far as I can tell in this case, we've got these 5 forces acting on this ladder, and that's all. So we have already at this point taken our second step on here, and I think that's complete. So now we're going to go up here, define coordinates, and simply see how this works. So why not? Let's do our conventional Cartesian choice. X positive to the right horizontally, y positive vertically upwards. And torques, well, maybe I will take torques as positive in the counterclockwise direction. Okay, so there's my chosen coordinate choice. My preference, as always, but once I've made this choice, I want to stick with it. And then we're going to go ahead, resolve any forces. We have to do our equations. So let's see how this looks. All right, so let's look at Fx net 0. Then Fy net equals 0. And then finally torque C net equals 0. Okay. So I'm going to go through this fairly quickly. It's pretty straightforward. So looking at the x forces, we have plus Fs acting at the bottom, minus NW at the top. So those are the 2 forces only that are acting horizontally. Net force equals 0. That one's pretty straightforward. The next one also is going to be pretty straightforward. Plus NF minus WL minus WP equals 0. Again, hopefully straightforward. Let me just pause there and ask if anyone has questions on those 2. Okay. So the third one's slightly more interesting because when we're talking about torques, of course, we have to be defining torques about a particular potential axis of rotation. Now, of course, in statics, nothing is rotating, so that seems slightly strange, but as you know, whenever we're dealing with angular quantities, including torques, we have to have a defined reference point to be calculating those torques about. So we do need to define a point. And this is perhaps almost the only piece of advice I have for solving these problems, which is, in principle, net torque equals 0 constraint has to be true about any point on this object. But to make our life a little easier, and make our algebraic life a little bit easier, you'll often find it advantageous to choose a point that has one or more of the unknown forces acting through it, or at least its line of action passing through it, simply because it's not going to contribute to the torque. So in that sense, you are going to make your life easier. So let me just make that as a footnote here. Often advantageous to choose my pivot. Of course, this thing isn't rotating at a point where one or more unknown forces acts. So, with that in mind, what might you choose as a reference point to calculate the net torque about that point as being 0? Again, you can choose any. Yeah?
The point where the floor and the ladder touch.
Yeah. So that would be my choice as well, because we don't yet know either of those 2 forces, the normal force exerted by the floor on the ladder, nor do we know the friction force. So I'm going to choose that point at the bottom of the ladder to do my torque calculation. Okay, so maybe I'm going to ask you to help me out with this because it's more complicated. So I've claimed that I'm going to make things that turn counterclockwise positive. So the 3 forces that have finite lever arms with respect to my axis / pivot point at the bottom of the ladder, the only one that potentially could turn this thing counterclockwise with respect to that point is NW. So I'm going to put this in with a plus, but of course I need to calculate the torque now. So I need the product of the force and its perpendicular lever arm, whichever way you like to calculate this. So with the parameters that I'm given here, what do I need to multiply NW by to get this to be correct? Let's see if we can get some new volunteers.
Yeah. Sine. Sure. Oh wait. First, NW is L, and then sine 40.
So sine 40. Let's work in terms of theta, if you don't mind.
Okay. 90 minus theta? Or is it just theta?
Want to commit?
I'm going to commit to 90 minus theta.
So you want the sine of 90 minus theta?
Yeah.
Okay. Let's see, let's go here.
I would think L sine theta.
And one more?
Same thing.
Same thing, okay. So L sine theta, which turns out to be the right choice. Remember, and again, you probably developed your own preferred way of doing this at this point, but we need to know the moment arm for this force to provide our torque. My preferred way is always to extend the line of action of the force and then define the perpendicular distance from my pivot to that line of action. So for me, I'd go that route. And with the parameters shown, indeed, that is L sine theta. So that would give me my first torque term, the only one that's tending to turn this counterclockwise. Now I need to fold in the other two with an appropriate minus sign. And I'm going to do this now because at this point we've kind of done the maybe slightly tricky part. So I'm going to claim now that the weight of the ladder is WL. And now I need the perpendicular moment arm, which I claim is D over 2 cosine theta. And then lastly, the weight of the person, and this goes to L over 2, thank you, yep. And then WP D cosine theta. Does that look okay? All right, so now we've got our three simultaneous equations for solving this, and as always, setting it up is the hard part, solving the simultaneous equations, hopefully less so. So in that sense, we are done. I might, sometimes, if any of you are having difficulty with these sorts of expressions, you might, if there are a lot of forces, a lot of torques acting, you might try and tabulate it in some form where you simply say, what is the force, what is the moment arm, what is the torque, and put it in that table with an appropriate sort of sign associated with it. But hopefully at this point you're pretty comfortable in writing it down directly. So let me just solve this quickly, but again, this is the hard part of this, and then we'll move right along. So what this tells us is, let's see, what do we know here? So we know, I don't know either of these just yet, but we can relatively quickly get it. So we do know this, we do know this, so we can figure out this. So, okay, so we can get this. What do we know down here? So we don't get note of this, we do know this, we do know this, this, and this. I think that's right. So in principle then we can get this, and then once we've got this, we can get this. Okay, I know I was doing that quickly and probably hard to follow, but that's the sort of chain of solving that you're going to be going through. And so in fact, working from here, what I can say is from this one, the normal force of the wall on the ladder. I don't think I'm even going to put in numbers here, it's not a good use of our time. It turns out it's 727 newtons, and then when I plug that in over here, I can get, though it's not asked of us in this case, I can get that this is 727 newtons. And then, what else am I missing? the force from here. So this normal force off the floor is just the sum of these two things, 875 plus 355, what's that number? 1230. Okay. All right, so that came from here, and then this came from here. So this is pretty much the standard approach you're going to be taking. Rarely is there any more to it than this. It's just a little bit painstaking.